So we're going to look at my 31, year 32. This is again returning to the idea of parallel plates. And so we're going to start with two parallel plates like we normally do. And we're going to draw them in here. And they're going to go horizontally instead of vertically. And they're hanging out, and inside there's like a little pollen grain. So the pollen grain is not a subatomic particle. It's legitimately just dust or pollen. And there's some stuff we know about the pollen grain. For example, the pollen grain has a charge. So Q pollen is going to be equal to plus 1.5 picocoulombs. So it has charge, a lot more charge than, say, a single electron. And it is suspended between these two plates, which means it's just kind of hanging in space. And the only thing that could cause it to hang in space is if you think about scuba divers or things in water, they establish neutral buoyancy in water. So this thing has neutral buoyancy in the atmosphere, and the only way it can do that is the same way that things floating in water do it, and that's to have a balanced set of forces above and below it. So our pollen grain here has some forces acting on it. It definitely is large enough that it has weight, so there's going to be some mg component. And then to counteract that on the pollen grain, there must be an equal force and magnitude from an electric field. So an electric field, a positive charge would experience an upward force. So the electric field we are going to draw that the pollen grain experiences is one that goes from the bottom plate up to the top. And that is the electric field it is in, because a positive charge would follow that path. And we actually do have a positively charged pollen grain. So the bottom plate we know to be positive, the top plate we know to be negative, and the charge density we actually know as well. It is given to us as 1 microcoulomb per meter squared. So this is all just some setup for this problem. And they ask the big question of, great, you know the charge of the pollen grain, what's the mass of the pollen grain? And so that's what we're being tasked with. Well, we can take what we know from Newton's second law and set up, if up is the positive direction, the following relationship. Minus mg is equal to ma, where m is the mass of the pollen. So there's an electric force up, its weight is pointed down, that's why this has got a negative sign hanging out in front of it, and then that is equal to the object's mass times its acceleration. However, the object's not moving, it's suspended, it's levitating, so that means it's not accelerating, so this part just goes away as 0. And what we end up with is just kind of a nice balanced electric force equals the object's weight. That allows us to find m quite easily, because we can take the electric force and divide it by g, and that will give us m. So the big question is, well, what's the electric force? Well, we know that the electric force from parallel plates is going to be equal to the charge times the electric field from parallel plates, and we know that from previous examples is just the charge density divided by epsilon naught. That is a horrible epsilon, it just looks like a lowercase e. That's not much better, looks like a claw, but we're going to go with it. And so that's epsilon naught. So if we know that that is the electric force, we can combine this piece and this piece, and we can get something along the lines of Q sigma divided by G epsilon naught is equal to the mass. And that's what we want. That's where we want to be for determining our our mass of our pollen grain. So we know the charge is 1.5 picocoulombs. That's times the 1 microcoulomb per meter squared charge density. And then we'll divide that by G, which we'll assume to just be 9.81 meters per second squared. And then epsilon naught, remember, is 8.85 e to the negative 12th, with a bunch of units that are going to cancel out, leaving us with only kilograms. Well, we're able to determine a mass then. This equals 1.73, doing some rounding, e to the negative 8th kilograms. So that's really, really small. And remember, this is in kilograms. You might be tempted to, call it, like 17 nanokilograms, but don't. It's just 1.7 times 10 to the negative 8 kilograms. You have to multiply, it'd be 17 nanograms, and then you need to go divide that by 1,000. You'd end up with 17 picograms. It's pretty close to the charge, actually. Shouldn't be too surprising, but as far as the exponent is concerned, that shouldn't be too surprising. So that's the first part. So that's the first part, and then there's other stuff. Let's see. Other grains of dust would also be suspended by this device. For example, if a dust grain had twice the mass of the original grain and was also suspended, what would be the charge of this other grain? So for this to be balanced, we would return back to this relationship. So if there is a dust grain that has twice the mass of the original, it would have to have twice the charge of the original. And that comes from this pretty straightforward Q and M are proportional. They're just equal. It's not even by a factor or inversely proportional. Just if M goes up by 2, Q has to go up by 2 as well. And they ask, well, then what's the charge to mass ratio for all the grains? So that they want to know essentially what is, or mass to charge ratio or charge to mass ratio. You can do it different ways. If you do the mass over the charge and you want that ratio, what's that going to look like? Well, it's going to be sigma over G epsilon naught. And so that's just a ratio that essentially says as long as the mass and the charge, the mass over the charge is going to be equal to that, no matter what. So
is that the answer then? What would be the charge of
that's
the other grain?
Well, the charge of the other grain would be twice the mass, and then this is just a relationship of mass over charge. That as long as the mass divided the charge is equal to this constant, it will be suspended. So that's that problem.